My name is Larry Kenney, and I'm a professor at Penn State University. It's good to be in a part of the world where climate change not only exists, but it's linked to health outcomes. We've all, in the US, gotten letters related to our federal funding telling us to eliminate those types of taboo words, or grants will not be funded in the future. So we're going to get this session started. We have a number of speakers. I'm going to lead things off and then turn it over. Hopefully we'll have time for a question or two. So welcome again. So I'm going to follow up first on some of the things that Professor Tipton mentioned, and that is that the heat strand, which all of you are attending today, will follow the general focus of the entire meeting, which is to try to shape the agenda, build global networks, turn evidence into impact. Any idea? Oh, there we go. So this is the general design of the meeting and the general problem. So with respect to this strand, the prominent problem, of course, is heat stress. And we want to get to this end of the spectrum where we're discussing heat resilience. We want to continue the communication, promote enduring change, all toward improved health and safety, especially in the workplace. And we'd like that to be the legacy of this summit. And thank you all for participating. The roadmap for getting us there really involves physiology, it involves mitigation, it involves aligning goals, it involves policy change. And so, again, this is an interactive meeting. These are the desired outcomes. So I've been asked to talk briefly about the role of physiology in informing this type of action. I'm a physiologist, and as we think about how we can mitigate the impact of heat stress on human beings, one of the earliest questions to consider is, when should action be taken? Obviously, immediately. But from the respectiveness of human beings, we need to ask questions like, how hot and humid is too hot and humid for safety? How hot and humid is too hot and humid to maintain productivity in the workplace? How hot and humid is too hot and humid for physical and mental well-being? And that's really the direction I'm going to lay out for this strand. From a physiological perspective, we can divide all of these considerations into things we measure in the environment: air temperature, humidity, radiant heat, air movement, the work itself, the intensity, the type, the duration, work-rest cycles, and then very importantly, the person in terms of sex, age, body size, fitness, acclimation, clothing, comorbidities. It's really a relatively complex problem to bring these all together and try to determine those issues of how hot and humid really is too hot and humid for safety. And so people have developed, proposed, refined a whole series of heat stress indices. What should we measure? Is there a single number that we can put our hats on to say, this is the number beyond which action must be taken from a physiological perspective? You can see, if you can see the small print, 1905 was the first proposed heat stress index, wet bulb temperature. And it goes all the way up to 2012 with the Universal Thermal Climate Index developed here in Europe. Sorry, it's a little bit of a delay. There we go. So one of the easiest climate change indices that people have used worldwide to determine when action should be changes is wet bulb globe temperature. Wet bulb globe temperature is a combination of the wet bulb temperature, a measure of the ability of sweat to evaporate, globe temperature, a measure of the radiant heat, and then dry bulb temperature. And it can be simply measured, which defines some of the reasons why it's used so widely, by having 3 different thermometers, one inside a black globe, one wetted with a wick to determine its ability to evaporate, and then a simple dry bulb thermometer. So this is really easy to measure the environment itself. But what about people? Once you determine the WBGT, or indoors, the wet bulb temperature, what do you do with it? So the problem is WBGT doesn't really consider the person or the physiology. How hard are people working? Are they acclimatized to the heat? How fit are they? Is there ventilation? In some industrial applications, are they required to wear protective clothing? So from a physiological standpoint, WBGT really is an initial measure of the environment, but then where do we go with it? So the Universal Thermal Climate Index is widely used in Europe, not used in the US much at all. And really, it's a function of the dry bulb temperature, the radiant heat, the air movement, and the relative humidity. The good thing about UTCI is that it is based on a physiological model, and it's been developed with quite a bit of care, but it has some negatives as well in terms of how hard it is to measure and base decisions on it. And in fact, UTCI in most work applications is not all that different from WBGT. So over the past 6 years or so, we have undertaken a project to determine physiologically how hot and humid is too hot and humid. And we call it the Penn State Human Environmental Age Threshold, or HEAT program. And it combines physiology and biophysics, but has involved an intense series of laboratory climate chamber-based tests. So what we do in these series of studies, and I show you this to set up the next slide or two, is that we put human beings in environmental chambers. Our major impetus for doing this work has been the aging population. And so we've tested about 600 people aged 18 to 97 in our environmental chambers. We put them in the chamber, and then we, in some experiments, keep the temperature constant. In this case, it would be 34 degrees centigrade. And then after 20 minutes, we start to increase the humidity step by step by step. In other experiments, we keep the humidity constant, and we start to increase the temperature in that stepwise fashion. And if you monitor people's core temperatures that you see there in the top open circles, their temperature goes up, and across a wide range of temperatures, air temperatures and humidities, their temperature rate remains relatively stable. We can maintain our body core temperatures and our heart rates across a wide range of temperatures and humidity combinations until we get to some critical combination of temperature and humidity, beyond which heat gain and production exceeds our ability to lose that heat, and then core temperature will rise progressively. And so in this particular case, that critical temperature for this one individual subject is a dry bulb temperature of 34 degrees and 66% relative humidity. And if you test enough people, you can create these sorts of safety charts. So this happens to be for young men and women under the age of 35. doing light desktop type work, no radiant heat, they're indoors, and minimum air movement. And you can see there are a whole range of temperatures and humidities shown here in green that we call compensable. That is, they can maintain their core temperature at a relatively stable level. In red are a whole range, the whole gamut of temperatures and humidities that are uncompensable. Core temperatures are going to continue to rise. And the white area between those two is the 95% confidence interval. These are for young, healthy men and women. The yellow line that you see there is what we see for older men and women. And so that safety margin decreases dramatically as we age. So these types of physiological approaches can be used to help answer that question, how hot and humid is too hot and humid for any given metabolic heat production. If you take those, what we call those livable limits, and you look over the past decade at where those have shown up in the world, you can see these red dots. These are areas of the world where there have been extended periods of time in which people have been in those unlivable, uncompensable conditions, just going about activities of daily living. You can see that they cluster around bodies of water because as air temperature increases, it holds more water vapor, and the greatest threats in the future in terms of heat waves will be humid heat events and not dry heat events. You can also look at annual hours in those unlivable conditions. So what you see as the colors progress and get darker toward red are the number of hours people will be living in those conditions with a 1.5 degree increase in global temperature on the left, 2, 3, and 4 degrees C projected increases in mean global temperature. And again, what I'm showing you are for young, healthy subjects doing fairly light activity. What are our chances of staying in that 1.5 degree? Not good. Previous speakers have talked about that topic. We can also look at it another way, which is at those various global warming targets, what are the affected population estimates of people that will be in exceedance of those livability temperatures and humidities for 1 week, shown there in the black, for 1 month, shown in the blue, and for 3 months, shown in the red. So, as mentioned this morning, with estimates in the 3 to 4 degree global warming target range, we're talking about somewhere on the order of 1.5 to almost 3 billion people living under those conditions for long periods of time.